Hello everyone. In this video, I'm going to be talking about a study by Shadlen and Newsome from 1996 that they published in Proceedings of the National Academy of Sciences under the title Seeing and Deciding. On a daily basis, our brain integrates sensory information, such as visual, auditory, and motor inputs, to make decisions regarding simple choices and even complex behaviors. This study focuses on how the primate brain achieves this, specifically examining how neurons in the lateral intraparietal area, or LIP for short, associate sensory input with specific motor output. In this case, saccades, which are eye movements, and what this reveals about the neural encodings of decision-making. The primary question addressed in this study is how the brain uses sensory cues to make informed decisions. Two rhesus monkeys were presented with a motion discrimination task. They viewed displays of moving dots, with some dots moving coherently in one direction and other randomly as noise. The monkeys were tasked with determining the direction of motion and indicating their choice by making quick eye movement, or saccade, towards one of the targets. This setup allowed researchers to record lip neuron activity and analyze its role in the decision-making process. Each trial began with the monkeys fixating on a point while the target options appeared. After a brief delay, the dot motion stimulus was shown for 2 seconds. Following another short delay, the monkey made a saccade to indicate its choice of motion direction. Figure 1 illustrates the firing patterns of a single lip neuron at different levels of motion coherence: 51.2%, 12.8%, and 0% coherence or random motion. Each coherence level has two conditions. The left column shows trials with the monkey's choice aligned with the neuron's movement field, known as target 1, while the right column shows trials where the choice was away from this movement field, known as target 2, which is on the right. Vertical lines indicate the duration of the motion stimulus, followed by a delay period before the monkey makes an eye movement to indicate its decision, which are marked with a circumflex symbol for each individual trial. The results show that lip neuron activity is higher when the motion is directed towards the neuron's movement field, with firing rates increasing even before the eye movement. This suggests that lip neurons don't merely execute movements, they also accumulate sensory information to inform the decision, integrating signals over time. Now for figure 2, the researchers analyzed firing rates for different conditions at low coherence level of 6.4%, where the task was challenging and the errors were common. The dashed lines here represent incorrect trials, where the monkey made an error, and the green lines correspond to T1 choices, while red lines correspond to T2 choices. From this graph, we can conclude that the lip neuron activity not only represents the monkey's chosen direction, but also the quality of that choice, as follows. For T1 trials representing the green lines, when the motion is directed towards the neuron's preferred area, the neuron fires more strongly on correct trials, reflecting the monkey's higher confidence in a choice that matches the neuron's preference. On incorrect trials, though, the neurons fires less, suggesting lower confidence. For T2 trials representing the red lines, when the motion is directed away from the neuron's preferred area, the neurons fires more on error trials. This increased activity happens because the monkey incorrectly believes that the motion matches the neuron's preferred direction T1, indicating uncertainty or doubt about the T2 direction. In short, lip neurons signal both the direction of the choice and the level of confidence, with higher activity when the monkey feels more certain about the choice that aligns with the neuron's preferred direction. To conclude, the study shows that lip neurons play a crucial role in bridging sensory perception and action by integrating motion signals. Their activity encodes both the direction and certainty of the choice, providing insights into how the brain processes sensory information to support decisions. This offers a potential neural basis for decision-making, where lip neurons accumulate sensory evidence with a degree of certainty that influences the final decision. Thank you for listening. If you have any questions, feel free to ask. Thank you.